Welcome to the world of digital electronics, where logic meets innovation to power modern technology. Combinational logic is a class of digital circuits where the output depends only on the current input values. There is no memory element and no clocked state inside the logic. In other words, it behaves like a stateless Boolean function written as y equals f of x. These circuits are built using basic logic gates like AND, OR, NOT, NAND, NOR, and XOR, along with data selectors such as multiplexers. Using these building blocks, we create key hardware modules including decoders and encoders, adders, comparators, and shifters. When designing combinational logic, our primary goals are correctness first, followed by minimum delay and efficient area and power. In RTL, we typically implement combinational logic using continuous assignments, or always comb, to ensure latch-free coding. Now, why does combinational logic design matter? It forms the core of data paths and control decoding in ASIC, FPGA, and SoC designs. When we design combinational logic, our key goals are correctness first, then minimal delay, efficient area and power, and hazard-safe behavior. In practice, we implement these functions either as gate-level networks or in RTL using continuous assignments or always comb, and then synthesis tools optimize the final hardware. Here is the roadmap of standard combinational logic topics we will learn in this course. We'll begin with the foundations: logic gates, Boolean algebra, De Morgan's laws, and NAND or NOR-only implementations. Next, we move into arithmetic, covering half and full adders, ripple carry adders, and the adder subtractor. Then we'll cover decode and encode blocks such as decoders, encoders, and priority encoders. After that comes data routing, including multiplexers, demultiplexers, and tri-state concepts with safe usage practices. We also study comparison circuits like equality and magnitude comparators, followed by shifting circuits including logical and arithmetic shifts and barrel shifters. Next, we handle code conversion and checking, such as gray to binary, BCD, 7-segment decoding, and parity. Finally, we look at system-level blocks like a small ALU, decoder plus OR plane structures, and LUT or ROM mapping. Throughout all topics, we also focus on quality aspects like logic minimization, timing and critical paths, hazards and glitches, and latch-free RTL design. Basics like Boolean algebra, gates, etc. Discussed part, previous learning session, please revisit. A half-adder is a combinational circuit that adds two 1-bit inputs, A and B. It generates two outputs, sum, which is the 1-bit result, and carry, which indicates whether a carry is produced. From the truth table, when A and B are different, the sum becomes 1, and when they are the same, the sum becomes 0. That behavior matches the XOR function, so sum equals A XOR B, which can also be written as A prime B plus AB prime. For the carry, O, it becomes 1 only in one case, when both A and B are 1, so carry equals A and B. It's called a half-adder because there is no carry-in input. When we include a carry-in, it becomes a full adder. Now let's look at the half-adder at the gate level and verify it using the waveform. On the left, the circuit is built using two basic gates. The sum output is generated by an XOR gate, so S equals A XOR B, which is also the same as AB plus AB. The carry output is generated by an AND gate, so C equals A and B, or simply AB. On the right, the waveform confirms this behavior across the 4 input cases. When A and B are different, the sum goes high and the carry stays low. Only when both A and B are high, the sum becomes 0, and the carry produces a 1. This matches the truth table and the Boolean equations perfectly. A full adder is a combinational circuit that performs 1-bit binary addition of 3 inputs, A, B, and the carry-in, sin. It produces 2 outputs, sum, which is the least significant bit of the result, and carry-out, which is the carry forwarded to the next higher bit position. If you look at the truth table, the sum output toggles based on whether the total number of ones in A, B, and sin is odd. That's why the sum equation is S equals A XOR B XOR sin. Carryout becomes 1 whenever at least 2 of the 3 inputs are 1 or even number of ones. So the carry equation is the majority function. Count equals AB plus A sin plus B sin. This full adder is the fundamental building block for multi-bit adders like ripple carry and carry look-ahead, and it is widely used in ALUs, address generation, arithmetic data paths, and accumulators. Now let's see how a full adder is built at the gate level. A full adder can be implemented using 2 half adders plus an OR gate. In the first half adder, we add A and B. This produces an intermediate sum and a carry, often called S1 and C1. Next, the second half adder adds that intermediate sum S1 with the carry in, sin. This generates the final sum output. That's why the final sum equation becomes sum equals A XOR B XOR sin. Finally, we generate the overall carryout by combining the 2 carry signals. If either the first half adder produces a carry or the second half adder produces a carry, we need to carry to the next bit. So we OR them together to get carry out. This matches the carry equation. Count equals AB plus A sin plus B sin. So the main takeaway is 2 half adders compute the sum, and the carry out is the OR of the 2 carry paths. In this slide, we are observing the waveform example of a full adder. On the left side, we have the input signals, A, B, and sin, which is the carry input. On the right side, we see the output signals, sum and carry plotted against time. As the inputs change at different time intervals, the full adder performs binary addition of the 3 inputs. Remember, the fundamental equations are sum equals A XOR B XOR sin. Carry equals AB plus B sin plus A sin. Notice how the sum output toggles whenever there is an odd number of logic ones at the inputs. The carry output becomes high whenever at least 2 inputs are high. For example, when A and B are high, carry goes high regardless of sin. Similarly, when all 3 inputs are high, sum becomes 1 and carry remains 1. This waveform verifies the logical correctness of the full adder operation across multiple input combinations. Now let's move to the ripple carry adder, or RCA. A ripple carry adder is an n-bit combinational adder built by connecting n full adders in series. The key idea is simple. The carry out from each bit becomes the carry in for the next higher bit. Because the carry has to pass stage by stage from the LSB to the MSB, we say the carry ripples through the adder. The inputs are 2 n-bit numbers, A n-1 to 0 and B n-1 to 0, along with an optional sin. The outputs are the sum n-1 to 0 and the final count. For each bit position I, the sum is SI equals AI XOR BI XOR CI, and the carry to the next stage is CI plus 1 equals AIBI plus AICI plus BICI. The carry chain starts with C0 equals sin and ends with Cn equals count. So the RCA is very easy to design and understand, but its main limitation is speed, because the final result depends on how fast the carry can ripple across all n stages. Summarize the ripple carry adder with its key advantage and limitation. The biggest advantage of a ripple adder is that it's simple and compact. It's easy to design, easy to code in RTL, and easy for synthesis tools to optimize. Because of that simplicity, ripple adders are commonly used for small bit width adders like 4, 8, or 16 bits, and also in blocks like counters and address increment logic where the timing is not extremely tight. The main limitation is timing. In the worst case, the carry has to propagate through every full adder stage from the least significant bit all the way to the most significant bit. That means the critical path is roughly n full adder carry delays, and the delay increases linearly with n, which we write as TRCA equals n times t carry of a full adder. That is why high-performance designs typically move to faster structures like carry look-ahead or prefix adders. Let's look at the half subtractor. A half subtractor performs one-bit subtraction. It subtracts b from a, so the operation is a minus b. It produces two outputs, the difference, labeled d, and the daro, labeled bout. From the truth table, the difference is 1 whenever a and b are different, and 0 when they are the same. So the difference equation is simply d equals a XOR b. The borrow becomes 1 only in one case, when a is 0 and b is 1, meaning we don't have enough value in a to subtract b. So we must borrow from the next higher bit. That's why the borrow equation is bout equals a prime and b. So the key takeaway is difference behaves like XOR, and borrow indicates the specific condition where a is smaller than b. Now let's connect the half subtractor gate-level circuit with its waveform. On the left, the half subtractor subtracts b from a and produces two outputs, difference and borrow. The difference is generated using an XOR gate, so d equals a XOR b. This means the difference is 1 when a and b are different. For the borrow, we first invert a and then AND it with b. So borrow equals a prime and b. This borrow becomes 1 only when a is 0 and b is 1, meaning a is not sufficient to subtract b and we need to borrow from the next higher bit. On the right, the waveform confirms this behavior. As a and b change through all four combinations, the difference waveform follows XOR, and the borrow waveform goes high only in the a equals 0, b equals 1 interval. This matches the truth table and Boolean expressions exactly. Now let's understand the full subtractor. A full subtractor performs one-bit subtraction with borrowing. It subtracts b and the borrow-in, bin, from a. So the operation is a minus b minus bin. It produces two outputs, the difference, d, and the borrow out, bout. From the truth table, the difference behaves like XOR across all three inputs. So the difference equation is d equals a XOR b XOR bin. The borrow out becomes 1 whenever a does not have enough value to subtract b and bin. In other words, borrow is generated when either b is 1 while a is 0, or bin is 1 while a is 0, or when both b and bin are 1. That gives the borrow equation, bout equals a prime b plus a prime bin. So the key takeaway is, difference is a 3-input XOR, and borrow out indicates when the subtraction needs a borrow from the next higher bit. Let's look at the gate-level implementation of a full subtractor. This circuit is built using two half subtractors and one OR gate, similar to how a full adder can be built from two half adders. In the first half subtractor block, we subtract b from a. This produces an intermediate difference, call it d1, and a borrow b1. Next, the second half subtractor takes that intermediate difference d1 and subtracts the borrow in bin. This produces the final difference output d. and another borrow B2. Finally, the overall borrow out, BOUT, is generated by combining the two borrow signals. If either stage needs a borrow, the full subtractor must borrow from the next higher bit. So we OR them together. BOUT equals B1 or B2. So the takeaway is, two half subtractors generate the final difference, and the borrow out is the OR of the borrow paths. Let's verify the full subtractor behavior using this waveform. At the top, the three inputs A, B, and bin change over time, covering the combinations from 0, 0, 0 to 1, 1, 1. For each interval, the difference output D is computed as a three-input XOR. D equals A XOR B XOR bin, so D becomes 1 whenever an odd number of inputs are 1. Next, observe the borrow out, BOUT waveform. BOUT goes high whenever the subtraction needs to borrow from the next higher bit. Practically, borrow occurs when A is not sufficient to subtract B and bin. This matches the Boolean expression, BOUT equals A prime B plus A prime bin. So when A is 0 and either B or bin is 1, BOUT becomes 1. Also, when both B and bin are 1, borrow is required unless A is also 1. Overall, the waveform confirms the full subtractor truth table. The difference follows XOR behavior, and the borrow output flags exactly the intervals where a borrow is needed. Now let's understand the adder-subtractor circuit. An adder-subtractor is a single digital block that can perform both addition and subtraction on two binary numbers, typically using 2's complement for subtraction. In this 4-bit example, the core is a chain of 4 full adders connected in series. Each full adder takes 1 bit of A, a modified version of B, and a carry-in, then produces a sum or difference bit and a carry-out to the next stage. The key control here is the adder-subtractor selection line. That control is fed into XOR gates on each B bit. When the control is 0, B passes through unchanged, and the circuit performs A plus B. When the control is 1, each B bit is inverted through the XOR, and we also apply a carry-in of 1 at the least significant stage. That adds the plus 1 required for 2's complement, so the adder effectively computes A plus B or plus 1, which equals A minus B. So with one control signal, the same ripple full adder chain can generate either a sum or a difference, and the final carryout can also be interpreted as a borrow indicator in subtraction. Now let's understand what a decoder is. A decoder is a combinational logic circuit that takes n binary input lines and converts them into 2 to the power n unique output lines. The important point is, for any given input combination, only one output becomes active. So the key idea is, binary input gets converted into a one-hot output, meaning exactly one output is 1, and all the remaining outputs stay 0. In general, the inputs are labeled as AN-1 down to A0, and the outputs are labeled as Y0 up to Y2 to the power n-1. The rule is simple. Number of outputs equals 2 raised to the number of inputs. For example, if we have 2 inputs, we get 4 outputs. That's a 2 to 4 decoder. If we have 3 inputs, we get 8 outputs. That's a 3 to 8 decoder. So decoders are mainly used whenever we want to select exactly one line based on a binary input, like in memory selection, address decoding, or control signal generation. Look at the 2 to 4 line decoder. Here we have 2 inputs, A and B, and we get 4 outputs, Y0, Y1, Y2, and Y3. Because it is a decoder, it follows the one-hot rule. For any input combination, only one output will be 1, and all others will be 0. Let's verify using the truth table. When A is 0 and B is 0, output Y0 becomes 1. When A is 0 and B is 1, output Y1 becomes 1. When A is 1 and B is 0, output Y2 becomes 1. When A is 1 and B is 1, output Y3 becomes 1. So you can see clearly, exactly one output is active for each input. Now the Boolean expressions for the outputs are Y0 equals ABB, Y1 equals AB, Y2 equals AB. And one more important property. Since only one output is active at a time, Y0 plus Y1 plus Y2 plus Y3 equals 1 for all valid inputs. That's why a 2 to 4 decoder is commonly used for selection and address decoding, where we want to activate exactly one line based on the input. Understand the 2 to 4 decoder circuit implementation using logic gates. We have two inputs, A and B. First, we generate the complements using NOT gates, A' and B'. Next, we use 4 AND gates, and each AND gate creates one minterm which becomes one decoder output. Y0 equals A', B'. Y1 equals A', B'. Y2 equals A, B'. Y3 equals A, B'. So, the idea is simple. Each output corresponds to exactly one input combination, and only that AND gate becomes active. For example, if A equals 0 and B equals 1, then A' equals 1 and B equals 1. Therefore, Y1 becomes 1, while the other outputs remain 0. On the right side, we showcase an OR gate, combining the outputs as Y equals Y0 plus Y1 plus Y2 plus Y3. In a true decoder, we typically utilize the individual outputs, Y0 to Y3 directly. However, this OR is merely to illustrate that the outputs collectively cover all input cases. Hence, this circuit distinctly demonstrates how a decoder is constructed. Invert inputs, form minterms using AND gates, obtain one-hot outputs. ... This is an example of a 2 to 4 decoder. Please try to design different decoders based on the general design steps, which we have already discussed. But next, in minutes, we will discuss again, followed by the implementation of large input and output combinations from small inputs and outputs. Now let's look at the general design steps for any decoder, where n inputs produce 2 to the power n outputs. Step 1 is to decide the specification. First, confirm the number of inputs, which we represent as an-1 down to a0. Then confirm the number of outputs, which will be 2 to the power n, labeled y0, up to y2 to the power n-1. In this step, we also decide two important design choices. 1, are the outputs active high or active low? And 2, do we have an enable pin E or not? Enable is used to activate or disable the decoder based on system requirement. Step 2 is to write the truth table. We list all possible input combinations, starting from 0 up to 2 to the power n-1. And for each input row, the decoder must follow the one-hot rule. Exactly one output should be 1, and all other outputs should be 0. If it is an active low decoder, then the logic is reversed. For each input combination, exactly one output becomes 0, and the remaining outputs stay 1. So these two steps give us the foundation. First, define the interface and behavior, and then capture it clearly using the truth table. Next, let's move to Step 3 and Step 4 in general decoder design. Step 3 is assign output numbers to minterms. Here, the idea is very straightforward. The output index, k, directly matches the binary value of the inputs. So if the input combination equals binary k, then yk becomes 1. For example, when n equals 3, we have 3 inputs and 8 outputs. So the mapping becomes 0, 0, 0 activates Y0, 0, 0, 1 activates Y1, and so on, up to 1, 1, 1 activates Y7. Now step 4 is derive the Boolean equation for each output. For every output yk, we take the input pattern that activates it. Then we apply a simple rule. If a bit is 0, we use the complement of that input. If a bit is 1, we use the true form of that input. Let's take the example shown here. If k equals 5, the input pattern is 101 for inputs A, B, C. That means A equals 1, use A, B equals 0, use B prime. C equals 1, use C. So the output equation becomes y5 equals AB prime C. So in general, every decoder output is simply a minterm, which is an AND product of literals that exactly matches that input combination. Now let's continue with Step 5 and Step 6 of the general decoder design. Step 5 is implement using gates, the direct method. Once we have the Boolean equations, implementation is straightforward. First, we create the complements of all inputs using NOT gates, like A prime, B prime, C prime, and so on. Then, we use 2 to the power n AND gates. Every AND gate implements one minterm, and that directly produces one output line, y0 to y2n minus 1. An OR gate is usually not needed in a decoder because we use the one-hot outputs individually. We add OR only if we want some combined signal for a special purpose. Next comes optimization. This becomes increasingly crucial when n is large. Instead of constructing 2 to the power n massive AND gates, we employ a hierarchical design. We split inputs into two groups, the MSB group and the LSB group. Then we do pre-decoding. Decode the MSBs first to generate enable lines. Decode the LSBs in parallel blocks to generate the final outputs. For example, a 4 to 16 decoder can be built as 1 2 to 4 decoder for the MSBs and 4 2 to 4 decoders for the LSBs. Finally, Step 6 is verification. Check the one-hot property. We confirm that for every input combination, only one output is active, and that the outputs cover all combinations with no missing or duplicate minterms. Let's see how to design a 3 to 8 decoder using smaller decoders. A 3 to 8 decoder has inputs A, B, C, and outputs Y0 to Y7. Instead of directly building 8 3-input AND gates, we use a hierarchical approach. First, we take the MSB input A and send it to a 1 to 2 decoder. This block produces two enable signals. One is active when A equals 0, that is A prime, and the other is active when A equals 1, that is A. Next, we use 2 to 4 decoders. Both of these 2 to 4 decoders take the same inputs B and C, but only one of them is enabled at a time. When A equals 0, the top 2 to 4 decoder is enabled using A prime. So it generates outputs Y0 to Y3 based on BC. When A equals 1, the bottom 2 to 4 decoder is enabled using A. So it generates outputs Y4 to Y7 based on BC. So effectively, A selects the output group, and B and C select the exact line inside that group. That's why we get Y0 to Y3 corresponding to input patterns 0BC, and Y4 to Y7 corresponding to input patterns 1BC. This is a clean and scalable decoder design, and it preserves the one-hot property. For every input combination, exactly one output becomes active. Understand how to design a 4 to 16 decoder using 2 to 4 decoders. A 4 to 16 decoder has 4 inputs, A, B, C, and 16 outputs, Y0 to Y15. Instead of implementing 16 4-input AND gates directly, we use a hierarchical decoder structure, which is cleaner and scalable. First, we take the two most significant inputs, A and B, and feed them into a 2 to 4 decoder. This block generates 4 enable lines, and only one of these enable lines becomes active depending on the value of AB. Next, we use 4 more 2 to 4 decoders for the lower two inputs, C and D. So inputs C and D are connected in parallel to all 4 decoders. Each of these 4 decoders is enabled by one of the enable lines coming from the first decoder. If AB equals 0, 0, the first enable line activates the first block, producing Y0 to Y3. If AB equals 0, 1, the second block is enabled, producing Y4 to Y7. If AB equals 10, the third block is enabled, producing Y8 to Y11. If AB equals 11, the fourth block is enabled, producing Y12 to Y15. So the logic is AB selects the group, and CD selects the exact output line inside that group. This way, for every input combination, exactly one output becomes active, maintaining the one-hot property. And that's why a 4 to 16 decoder can be efficiently built using 5 2 to 4 decoders. Now let's understand encoders. An encoder is a combinational circuit that converts a one-hot input into a binary code. In simple terms, if exactly one input line is high, the encoder outputs the binary index of that active input. That's why the typical form is a 2 to n encoder, like an 8 to 3 encoder. Here we use a standard example, a 4 to 2 encoder. The inputs are D0 to D3, and only one of them should be 1 at a time. The outputs are Y1 and Y0. From the truth table, if D0 is active, the output is 0, 0. If D1 is active, the output is 0, 1. If D2 is active, the output is 1, 0. If D3 is active, the output is 1, 1. That leads to simple Boolean equations. Y0 equals D1 plus D3. Y1 equals D2 plus D3. Look at the 4 to 2 encoder in terms of its block diagram and gate-level circuit. On the left is the block diagram. We have 4 one-hot inputs, D0, D1, D2, and D3, and the encoder produces 2 outputs, Y0 and Y1, which represent the binary code of the active input. On the right is the gate-level implementation. Notice that both outputs are generated using simple OR logic based on the truth table. Y0 is high when either D1 or D3 is high. So, Y0 equals D1 plus D3. Y1 is high when either D2 or D3 is high. So, Y1 equals D2 plus D3. So the main takeaway is that a basic encoder is very simple to implement. Just OR gates. But it assumes only one input is active at a time. Now let's extend the idea to an 8 to 3 encoder. Here we have 8 one-hot inputs, D0 through D7, and the encoder produces a 3-bit binary output, Y2, Y1, and Y0. The output represents the index of the active input. For example, if D0 is high, the output is 0, 0, 0. If D3 is high, the output is 0, 1, 1. And if D7 is high, the output is 1, 1, 1. From the one-hot truth table, we can directly write the Boolean equations for each output bit. Y0 is 1 for odd-numbered inputs, D1, D3, D5, and D7. So Y0 equal D1 plus D3 plus D5 plus D7. Y1 is 1 for inputs 2, 3, 6, and 7. So Y1 equal D2 plus D3 plus D6 plus D7. Y2 is 1 for inputs 4, 5, 6, and 7. So Y2 equal D4 plus D5 plus D6 plus D7. So the key point is, each output bit is simply an OR of the input lines that require that bit to be 1. This slide shows the 8 to 3 encoder using a block diagram and its gate-level implementation. On the left, the block diagram has 8 one-hot inputs, D0 through D7. The encoder converts the active input into a 3-bit binary output. that output should be labeled as Y2, Y1, and Y0. These 3 bits represent the index of the active input. On the right, the gate-level circuit is built using OR gates. Each output bit is simply the OR of specific input lines. Y0 is the OR of D1, D3, D5, and D7. Y1 is the OR of D2, D3, D6, and D7. Y2 is the OR of D4, D5, D6, and D7. So each OR gate collects the inputs that need that particular output bit to be 1. One important note: this is a basic encoder, so it assumes only one input is high at a time. Now let's understand the priority encoder. A priority encoder is a combinational circuit that converts multiple input request lines into a binary code, but with one key rule: it follows a fixed priority order. That means if more than one input becomes 1 at the same time, the circuit does not get confused. Instead, it encodes only the highest priority active input. Most priority encoders also provide a valid output, V, to indicate that at least one request is active. If all inputs are 0, then V becomes 0 and the output code is typically kept at a default value. Now, why do we need a priority encoder instead of a normal encoder? A basic encoder assumes a one-hot input, meaning only one line should be high. But in real hardware, like interrupts, arbitration, and request systems, multiple requests can happen simultaneously. So we need 2 things. First, a deterministic selection using priority, and second, a valid indicator to confirm that a request is present. Focus on the A-to-3 priority encoder. This is one of the most common priority encoder designs. It features 8 inputs, D7 down to D0, and it produces a 3-bit output Y?2?, along with a valid signal V. The priority rule? Oh, it's straightforward. D7 has the highest priority, while D0 has the lowest. So, the behavior is deterministic. If D7 is 1, the output code is 7, no matter what other inputs are doing. If D7 is 0, but D6 is 1, the output becomes 6. This continues down the list. If only D0 is 1, the output becomes 0. And if all inputs are 0, then no request is active. So the valid output V becomes 0, and the output code is typically held at a default value. So, the key takeaway is this: when multiple requests occur simultaneously, the priority encoder, without fail, always selects and encodes the highest priority request. Moreover, valid, that crucial signal, informs us whether any request exists at all. Now, this slide summarizes the 8-to-3 priority encoder using a compact truth table and the key conceptual equations. On the right, the table uses X to represent don't care inputs. This highlights the priority behavior clearly. For example, when D7 is 1, the output is always 1, 1, 1, regardless of what D6 down to D0 are doing. If D7 is 0, but D6 is 1, the output becomes 1, 1, 0, again ignoring lower priority inputs. This continues down until the lowest case, where only D0 is 1, producing 0, 0, 0. The valid signal V indicates whether any request is present. That's why its equation is simply the OR of all inputs. V equals D0 plus D1 plus D7. If all inputs are 0, then V becomes 0, and the output code is typically held at a default value. The important point is that the output bits depend on the highest asserted input, so unlike a simple encoder, we usually implement priority encoders using if-else chains or case priority logic, rather than simple OR equations.